the most important course in mechanical engineering, and there are many subjects covered by this solid mechanics and beam theory, among many other subjects. Beam theory is the a core part. Why is that? Because most of the structures are supposed to support a vertical load. So most one-dimensional structures act like a beam. And in beam, there are two kinds of forces are developed. One is the shear force, and the other one is the bending moment. And the last class, we derived the two differential equations. One is for the shear force, and the other one is for the bending moment. So given force is the distributed load, which is a Q, a function of X, and we derived a differential equation which governs the shear force. So dV dx plus Q should be 0. And the second equation is from bending moment equilibrium, moment equilibrium, and dm dx plus V equal to 0. Those are two differential equations. And now here is the beam theory. Those two equations is just equilibrium equation for beam behavior, and here is the core part of beam theory. Okay, very much similar to torsion theory, where we started with observation of deformations. Do you remember that torsion, when we apply to torque to the shaft, and we first observe the deformation and what kind of deformation we will have, and we start with deformation and strains and stress and torque, right? Deformations and strains and stress and torque. That procedure should apply to most of the derivation of structural analysis. And same for beam theory. Okay, here is the beam. Okay, here is beam. And let's focus on bending moment only. Let's forget about the shear force. Okay, shear force. Do not consider shear force at this point. We just consider pure bending moment. Pure bending moment means that, let's say, if we don't have any shear force, V is 0, then moment is always constant from along the beam. So that is called pure bending moment. And let's say this is the beam and subject to a pure moment. Pure moment. Again, in pure moment status, bending moment does not change, is always constant. Any cross section has the constant bending moment. Well, these two equations is just a reminder of those two equilibrium equations. And now, let's say we observe the deformation. Okay? We apply bending moment at the two ends, and let's take a look at what kind of deformation we will have. Well, we have many subdivisions, and take a look at these all subdivisions, and there is one point, the center of curvature. All the deformations has a center point here, which means that when this beam is subject to a bending moment, it will have a constant curvature or a constant radius of curvatures. Okay, it is like a part of a circle, and which is a constant curvature. So anyhow, before going to a curvature, let's take a look at it. On the top surface and bottom surface, when it bends like that, what will happen to a top surface and what will happen to a bottom surface? Just two extreme cases. On the top surface, it will be a compress or a tension. It will be a compress, right? Yes? And how about the bottom part? It will be a tension, right? So keep that in mind. Those are two extreme cases. Okay? Keep that in mind. Those two extreme cases. Top surface will be a what? Will be what? Compressive. And bottom surface will be tension. Those two extreme cases will help you to proceed to next levels. So top is the compression and bottom is tension, and somewhere between this height, somewhere there should be zero line. See, top surface is subject to a compression, and bottom surface is the subject to a tension, and which means that the compressive or tensions is varying through the thickness, and there should be some line which should be zero strain, right? There should be some positions where we do not have any tension or we do not have any compression. Zero strain. Okay, we need to clarify the meaning of tension and compressions. Back to top surface. Okay, you said, well, we agree that there is the compressions. Compression in which direction? Compression in which direction? In x direction. This is the x and this is the y, right? So compression, it means that in x direction. And at the bottom is subject to a tension. Tension in which direction? In x directions. That's the very important concept. Okay. So in all these trains, we are observing in x direction. X direction means these directions. And top surface in x direction, x directional strain is the compress, and bottom is tension. And so somewhere between these, through the thickness, there should be some positions where x directional strain should be zero. Okay? This observation or so anyhow, top surface is the compression and bottom is the tension. Now let's try to little more clarify the use some symbols and definitions. Again, x-directional strain is simply defined as incremental displacement over original length. Let's take a look at here, and this is the some section and subject to a bending moment at left and right hand side, and this part will experience these deformations like that. And this vertical line, before deformation, it was a vertical line, and now after deform, this angle was a horizontal line, and then now it rotates by d theta And this one makes a curvature with the center here, and this should be d theta as well. Now, back to here. Here we say y, this line, the position is indicated by y. Okay, this is the line at y. And let's try to calculate length after deformation and length before deformations. That's the definition of extractional strain, right? So this is the before deformation, and this is the after deformation. And this is a d theta after deformation. And the original length, actually we are looking at this, let's say this is the AB, and this is the length before deformation, and this is the length after deformation. And I would say A prime and B prime. So length after means the length of the A prime, B prime, and length before means the A prime, A and B, the lengths. So back to here, and what is the length after deformations? Well, simply this is the d theta, okay? Simply this is a d theta, and this length is simply this radius times d theta, right? Right? Yeah. And what is the r prime? R prime is simply, this is the r. What is r? Well, we assume that this is the, where r, there is no strain. As we noticed in previous slide, at top is the subject to compression, bottom is subject to tension, and there must be a location where there is no extractional strain. And we just, these positions, okay, these positions indicate that, that location. So anyhow, let's say that is R. There is R here, and where we have a no axial strain. No axial strain means that this length is the same as this one. Okay, this length and this length is the same. So anyhow, what is the length of this one? Well, simply R minus, this is the what? This is the, right, this is the Y. So simply this length is what? A prime, B prime, this length is simply R prime d theta. 뽑아줘도 상관없나? Okay, so A prime, B prime is the length after deformation, and that's why we have the R minus Y d theta. And now, here is the key part. How about the length before? This one, before deformation, what was the length? Well, this one was simply this one, right? AB. And this AB length should be same as this line, right? And this line is same as that one. So simply AB before deformation is this one, and simply R times d theta. Okay? And this is the R d theta, and length before deformation is R d theta. And d theta is simply, we can drop this d theta, and R, we can drop them, and finally we have minus y over R. Okay, minus y over R. And K is called curvature, usually defined 1 over R. So anyhow, the epsilon xx, x-directional strain, is defined, is obtained as minus y over R. And do we know this R? We don't know yet. This R is surely related or caused by what causes this R? Moment. Well, yes, this moment will cause this R. So a moment will cause this R, and I'm sure that this curvature or R is also related to a cross-sectional information and material property as well. But anyhow, here M caused R, and how much we don't know yet. So, but what we know is that, okay, strain is proportional to Y. That is what we know. And now, what is R here? Okay, let's drive this R in terms of this d theta. Okay, let's say this is the 1 over R. R d theta equals simply dx. Because this line will be same as this one, and this is the R. So R d theta is simply dx. Okay? So from here, we simply R is, or 1 over R is, can be defined as d theta dx. Do we know, do we have this theta? Well, still theta is unknown. Instead of R, we use the theta. So anyhow, x-directional strain is now expressed minus y and d theta dx. Well, what is the d theta dx? Pay attention to here. D theta is the angle of rotation. Okay, this surface. This surface was vertical, and then subject to a bending moment, it rotates certain amount. It rotates d theta. So which means that d theta dx means that rate of the rotation of angle rotation. Okay, rate of angle rotation. Do you remember that gamma equal d phi dz r in torsion case? Well, very much similar to that observation. And d phi dz is the angle of rotations, like that. So angle of twisting rotation per unit length, and strain is proportional to r. And here, very much similar to this one, d theta dx is the along the length. This is the rate or angle of rotation per unit length. Angle of rotation means that this end surface will rotate like that, and it has a certain rate along the length, and that's the d theta dx. And there is the proportional strain is proportional to y. Okay, so this is the strain, and next, what is the next step? Next step is simply always deformation and strain and stress. Now, how to introduce stress? Well, simply we use these stress-strain relations, and since this strain is the axial strain, so the material property we need is Young's modulus E. So here, the E is missing here, right? And the sigma x is the along these directions. Well, we will have certain distributions, but in these directions and that directions, sigma y and sigma z is assumed to be 0. Why can we assume those two normal stress are 0? Well, compare the lengths in this direction and this direction and this direction. If the length is much larger than the other dimensions, then always in shorter direction the stress can be negligible always. So this is the H and this is the W or B, the width and height, and this H and B is much less than L. Then this normal stress can be assumed to be very small compared to extractional stress. Anyhow, that's the stress we have. Now, what is the next step? Next step is that use a moment in terms of a stress. Moment in terms of a stress. Okay, strain is the proportional to y. So stress is simply E times epsilon, and so it should be also proportional to y. So as you can see here, the top surface, I would like to draw this way. What this way is still okay. But anyhow, the stress, forget about this one, okay? The stress is proportional to this way, and those stress was caused by this bending moment M. And so anyhow, in this relation, we have this one. Okay, how do we get this one? Okay, let's say we have a certain stress applied to here at the location with y, and this is the sigma xx. And so first we multiply dA to have a force, right? This is the stress times A is the force. What is what was dA means? dA means this area. Okay? So sigma x times dA is a force, and then we need to multiply y to have moment. So sigma x times dA is the moment, the force, and times y is the moment, and integration is simply total moment we apply on this cross section. And why there is minus here? Well, simply this x and y, and this is the positive, right? This is the positive, and positive stress should go this way. But because we assume this is the moment, and this one is simply opposite to this moment. And that's why we have a minus sign here. Okay? Again, this is a positive side, positive portion, and in positive y and positive a x, and positive stress should be this way. And this stress would cause this one, this moment. And if, but we define this is the positive moment. Why is that? Because x, y, and z should be this way. So this bending moment is actually moment z with the component. That's why we have a minus here. Anyhow, this is the bending moment and stress relations, and now all we need to do is that we have sigma x, which was the E times rho and y. We just put it here. Okay, so y. So that's why we have a y here, twice of a y, and 1 over rho equals simply d theta dx, and that's why we have here and e, and there is a minus, and there is a minus, and so we will have a plus. And d theta dx is the just rate, constant rate. And can be out of integration. And if the material property is also constant, it can be out of integrations. But remember that if the material property is varying through the thickness, then it should be inside and integrate, considering variation of material properties. So anyhow, in this case, if the material property is constant, then it can be out of integrations. And now what are left here is that integrations y square dA. What is that? This is the moment of inertia. Area moment of inertia. So simply moment equal d theta dx ei. And what is unknown here? What is unknown here? Well, unknown was dx, d theta dx. So this is given ei. Okay? On the right-hand side, they are all known properties. M is the applied force, and E is the material property, and I is the cross-sectional properties. So now d theta dx, which was unknown at the very beginning, but that was obtained in terms of known values. That is the all about, this whole procedure is all about the beam theory. We put this equation back into here, then we will get stress. So simply minus EY, what was d theta dx? D theta dx was M EI, right? So E disappear and minus M and Y. That is the stress. That is the stress in cross-section. We have this, at the bottom we have a tension, and top we have a compression. And as you can see here, and plus y, here is the plus y, and plus y you have the, plus y you have compressions, and minus y you have the tension. And back to here, you can always calculate the strain as well. But in most cases, the stress is more important. Once you have a stress, and you can always calculate the strain. But remember that this strain distribution is nothing to do with the material properties. It's very much similar to a torsion case. In torsion case, always the gamma is linearly varying through the, from inner to outside. And the same here. The strain is always a linear function of y. And here is the stress. Actually, stress, you multiply the material property. And if the material property is a constant, this was simply canceled out. So anyhow, here is all the summary. And curvature, okay, curvature is the 1 over r. Which is same as the theta dx, and which is simply given m over ei. And stress-strain relations, simply stress equal E epsilon, and deformation strain is given like that, and bending stress is simply this way. It's a very famous equation, and which you have to fully understand. Okay. Now here, additionally, we need to study, they understand how to determine neutral axis. Neutral axis was that as defined a axis for no strain. Okay, no strain. This is the axis we define. And how do we calculate those that neutral axis? Yes, simply there was no external force Fx, and using this condition Fx equal to 0, that's how we determine the neutral axis. So sigma x, we already have them. We already drive the sigma x, which is this one, and E and R is the constant. So simply we have integration y dA should be 0. And that gives us how to determine neutral axis. Well, what does it mean? Integration y dA equals 0. Y needs to be located such that this should be 0. Then simply y equals 0 this is the located, this one should pass through centroid. Okay, centroid. The neutral axis is passing through the center of the gravity, or centroid. So in rectangular cross section, it always, this one is the neutral axis, and triangles neutral axis is also going passing through the centroid, which means that here, so always this is the, let's say this is the H, and this will be H over 3. Well, the reason is simply these cross sections, okay, this always stress is linearly varying, and so this will be a tension and this will be compressions, and total force should be 0, so this area should be equal to a bottom part. Okay. And here is the summary of the beam theory and comparison. Comparison between bar and shaft and beam. Okay, for bar and shaft and beam, there is the load. What kind of loads are applied to each case? And we have a force and moment, and in a bar case, we have axial force, Fx, can be positive or negative, and the shaft, we are applying the twisting moment, and in a beam, we applying shear force, either Fy or Fz. But in this X and Y case, usually Fy. And bending moment is the Fz, moment Z. That's the force. That's the force applied to a beam. Now, how about the stress? Well, there is a strain is missing here. Strain is simply FEA here. And stress is F over A. And shaft case, we have the gamma equal, what do we have? TR over IP and G. And this is the tau, TIPR. And this is the strain. And here, Y is missing here. And this is the stress. Again, in beam theory, this is stress, final form. And in shaft torsion theory, this is the final shear stress. That is the key part. And deformations, and simply delta is FL over AE or EA. And angle of rotations, TL over GIP. And the theta, which rotate, this is the amount of rotation. And which is the moment length over EI. Well, pay attention to all the deformations. They are very much look alike, right? And stress, even stress, very similar. Again, force divided by cross-sectional property and proportional to Y, and here proportional to R. So I would add one more row representing area properties, and here is I, and here is the IP, and here is the IZZ. And the last subject which we will cover later is the column. In column, the forces are always in compressed in longitudinal directions, axial directions, and the column is tend to buckle, and we will briefly cover this subject. Okay. Now we need to. Well, I'm sure you have already studied about the second order moment of inertia. And I just want to remind you this definition. And IZZ, you have certain cross-sections. Cross-section, and IZZ is simply, IZZ is defined as certain area and distance y, and y square and dA. And yy, you simply has a z here, and yz, you multiply yz. That's the this is a user called product moment of inertia. This is the third one. And this is a parallel axis theorem. And let's say you have a moment of inertia with respect to y and z, And what if you have, these cross sections moved by ZD and YD, which means that this moment of inertia with respect to this Y and Z axis. And condition is that Z axis pass through the centroid. Okay, this should be this axis should be pass through the centroid. In that case, this is the final form. Very important and very useful in many engineering problems, especially in our beam theory. And this is the just parallel axis theorem, which is the parallelly moved. But here is the different equation is called coordinate transformation. So we have the Y and Z, and what if we have rotated the axis, which was rotated by theta, and with respect to this axis. See again, Y and Z, we have I, YY, ZZ, and IYZ, and we have another new axis which rotates from YZ axis by theta. Then what calculate these three moment of inertia. Well, we just use the definitions. Y equals simply cosine theta Y plus sine theta Z, and Z equals simply minus sine theta Y plus cosine theta Z. We just use these relations, and using this definition, and we can drive. The final equation is like that. And as you notice that this is the exactly same as stress transformation. So you can simply use a Mohr circle to calculate this moment of inertia with respect to axis which rotate by theta. Okay, this equation, and again you can use the Mohr circle. So same concept as the stress and strains. Here you can define principal axis where YZ equals 0. No product exists. So only, this term can be 0. So only I, YY, and IZZ. Only those are non-zero. I, Y, Z can be 0. Those Y and Z axis is called principal axis. Like a shear stress, principal axis is defined such that there is no shear stress, right? So is the reason why there is a similarity or identity between this transformation and stress or strain transformation is that this is the simply second order tensor. Okay, mathematically it has the same characteristics, and that is the second order tensor. Well, I hope that you have this equation already in solid statics. And again, here is the Mohr circle for moment of inertia. Now, we drive the stress for the axial stress due to bending. Now, there is another stress, which is the shear stress. Okay, shear stress due to shear force. This is a little more complicated than bending stress. Bending stress is the sigma x, and this is the shear stress. Okay, let's back to beam subject to shear force and bending moment. And here is the V, and here is the V, and bending moment and bending moment. Let's assume that shear force is a constant. Previous, when we drive the beam theory, we assume that V is simply 0. Now we assume V is a constant. V constant means that we have an increment of the moment, right? Remember that this equation? If V is a constant, there is always increment. Non-zero moment increment. Okay, this is the case we're going to consider, and the point here is that we will calculate the tau xy or sigma xy due to this V, shear force. Okay, so moment caused the sigma x, and which was the MIY. That was the stress we derived. Now, what kind of a stress will be caused by this shear force? That's what we're going to drive here. Okay, pay attention here. This is a very important subject, and it's not easy. So you have to pay attention. And here we have moment x and moment, there is an increment dx here. Why? Again, if we have the V, we have a V, we always have increment. Moment should vary. So this stress will be I moment plus dm times y, and this stress should be I moment times y. So this stress and that stress is a little different. There's a little more stress. This sigma x, there's a little difference. Now, those increment, okay, keep that in mind. Why there is a moment increment? Huh? Why there is a moment increment? Because of this. See here, dm equal to minus dx v. If there is a v, which means that always moment has to increase. If v is 0, then the moment should be always constant. Okay, this is very important observation. Again, sigma x on the left hand side and sigma x on the right hand side, they are different. Why? Because there is the moment increment. But again, why do you have moment increment? Well, that is because we have a non-zero shear stress. So this non-zero shear stress, that is causing different sigma x. This one and they are different. Why? Because there is the shear force exists. Now let's go one step further. See again, here is the sigma x given moment I, and here sigma x moment, there is increment. Well, there is a minus there. See, this one and this one, they are different. Okay? They are different due to an increment of dm. See, this portion, we just cut this part. Okay? Just cut this part, and here is the part. And on the left-hand side, we have this much stress, and right-hand side, this much stress. And here, we should have some shear stress, right? See, here, we have the shear force, and that shear force would cause some kind of distribute shear stress and distribute the shear stress. And that is the distributed shear stress, tau sy and tau xy. And again, do you remember sigma xy should be always sigma yx? Right? Yes. Okay. So at that point, we have this much stress, and that should be same as this one. Right? Always at the right angle, this stress should be same as this one. So this should be same as this one, and this should be same as this one. Well, this is simply dx, and this one is the constant, and this magnitude should be same as the shear stress at that point, shear stress at that point. The shear stress, it may vary at the top. Here, same here. But at that point, the shear stress should be same as this one and same as this one. But this shear stress is constant. Why? Because this is just a small part. Okay. Now, let's say we apply force equilibrium. In which direction? X direction. X directional force. Okay, what kind of X direction? Okay, here, X directional force. What do we have? We have X directional force, this one, right? Now we want to consider X directional force. This is X directional force, this is X directional force. And is this one is X directional force? No. How about this? No. But how about this? This is the X directional force? Yes. So this one. So this, they are X directional force applied to this portion, and they have to be in force equilibrium. So this one, see, this part, this whole part, okay? So should be integrate over this area A, and left hand side, and this is the sigma x integration a. This is the same a here, and this one is representing this part, and should be 0. And this one is given like that, this one is given like that. And this one, incremental x-directional force at the bottom surface is given as, what is the B here? B is the width of this beam in this direction. And dx is the length, and sigma xy, which we want to drive. Okay? So we sum them up, and they need to be all 0. And here, dm is what? Given as minus dxv from equilibrium equation, right? So this term will disappear, and dm, we can put this into here. So here, and b times tau sigma xy b times sigma xy is this one. Remember this dm equal dxv. Okay, this is the where it comes from. And simply, okay, I'll write down here sigma xy equal I zz b and v integration y dA. That is the final equations, and this one we define as a Q. But remember, what's this definition of this one? Y dA. Y dA means that, let's say we want to calculate the shear stress at that point, then this is the Y. I mean, this A prime, integration A prime means that here, this is the integration y dA, A prime. The reason is that simply we integrate this part, right? This part, A. So y dA A prime is the, whenever we want to calculate, for instance, we want to calculate at this point y prime, then this part is the A prime integrations. So finally, if we integrate this part, then shear stress, as you can see here, shear stress is simply parabolic here and parabolic here, and all the shear stress. So at the top is a 0, and the downward and maximum, and like that. Here, the maximum at the center, and decrease, and 0. And as you can see here, the normal stress, this one has increased here, as you can see here. And again, if we cut this part, and this one, and this one, and this, they are in x-directional force equilibrium. Okay? This is how we calculate the shear stress at a certain point. And this is the VQ over IB. In rectangular cross section, the Q is simply defined as like that. You know, YDA is simply Y times B. And as you can see here, this is exactly parabolic distributions. If this is Y prime. So here and parabolic, and this is the maximum. And if we put the Y prime equals 0, then this is the, again, exactly 1/3. This is the V over BH is the average shear stress, averages, but the maximum is that tau maximum is the 1 point times tau averages. Okay, you have to remember that shear stress is always maximum at the middle and the parabolic distributions. Okay? Now, we derived two fundamental equations. One is the stress for bending stress, sigma x, and second is the shear stress when we have the shear force. Shear force is causing moment increment, and that moment increment will generate the x-directional force unbalance. And at the bottom, the surface, there should be some shear stress, and that shear stress is the same as this one. That's how we calculate these shear stress distributions. Okay, so any question?
shear 스트레스가 미들 포인트에서 항상 최고라고 했는데 그거는 사각형일 때만 삼각형이면 3분의 1 이쪽으로 이동하게 되는 건가요?
Right. Yes. The shear stress.
이것도 그럼 센트로이드 지나는 아까 그 밴딩 모멘트에서 센트로이드 지나는 축 설정할 수 있다고 하시잖아요. 그것처럼 이것도 그런 개념으로 보고 거기 축 지나는 데가 shear 스트레스가 최대라고.
Right. Yes. If you consider same steps, and you can simply, whether it is a rectangular, triangle, any cross section, all you need to do is you consider this Q. Calculate this Q and define as YDA. In this case, it's simply rectangular, but if you have the triangle, and you can redefine these integrations, and you will have the maximum at a different location. Okay? Okay, so this will complete our class today.